This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So I'll start the introduction to DSO project and operation amplifiers. So this introduction is just about the documents available on the LMS. Nothing more than that, but I will be teaching the blocks in the coming lectures. So what it covers is introduction to DSO projects, means what are the folders you will be seeing, so that when you get a folder, I don't want you to be getting panic, what is in the folder. So I'll be explaining the folder, the DSO folder. Then I will start operation amplifiers. So when we study operation amplifiers, then we will study filter design, and then I also will be teaching the DSO blocks in detail, how the signal is going through each block and what each block does. Then DSO project. So for designing the system, as a system engineer, when you are designing a system, electronic system, so what I meant is electronic system, there are mechanical systems, so what I meant is electronics part. So when you are designing an electronic system, then you will be using Altium for designing the system. So how you are using? So you will, as I said, when you want to measure the temperature of this room, then you will be having one block, that is a sensing part. You will be using some sensor, maybe a thermocouple for sensing. Then second block is amplifier. Maybe you are putting a filter, and then you got all these blocks. Then you will take Altium, and the Altium, when you open it, page number 1, then you will be making all these important blocks. You know what I meant? And then next page number 2. So what is the page number 2 means? Each block will be in the page number 2 expanded further, means the circuit inside. So for example, I will show you. So when you open the Altium, like this is a professional way, when you see some design, so you got some design from your manager when you are working in a company. So then when you open the Altium, what you will see is, for example, it is for measuring the temperature of this room. Then what you will see is a sensor part, a sensor block. That is a page number 1 on the Altium. So that is called a top level. So you will see the top level diagram on the Altium. So on the Altium, the top level diagram is the block level diagram. Then to measure the temperature of the room and storage. So then you got a sensor, then you got an amplifier block, and then maybe you got some processing part, and then you got some interface, and then this is the storage. So then here you got 1, 2, 3, 4 blocks. So this is the first thing you will see on the top when you open the Altium system, when you open the Altium file. Then when you got the page number 1, so this is a page number 1, you see the block level. So when you got the page number 2 means, then they will take this block 1, and then they will say this is a sensor, maybe this is a thermocouple, and then you got maybe some output. So here you got a thermocouple. And then page number 3, then maybe an amplifier. So you got an operation amplifier. So this may be X, that is a temperature, and then this may be Y. And then when you go to page number 3, this is a page number 3. So when you go to page number 3, they will be saying, okay, so here it is ground, maybe this is a buffer operation amplifier. They will say this is a Y, and then this is a Z. And then page number 4 means the circuit level diagram of this block. You know what I meant? On the page number 1, it's the entire block level diagram. That block you will be connecting like this. So here you will be seeing, so this is X, this is a Y, and then here you will say Y is going here to output. So that is Z. So it will become Z. So you will be connecting all the blocks properly. And then in the page number 2, then you will be designing what is the circuit inside each block. So that's how you will see a standard engineering design template. So here, this is an example of a DSO. which I made deliberately a little bit, blur, because that is your job to design it, how to connect it. So for the DSO, you will see around 10 blocks. These are the main 10 blocks. And then the figures are deliberately made not clear because students will be making blocks and connecting them part of assessment. And then, so there are 10 blocks. You should connect, like this block may be connecting to this one, this may be connecting to this one. So you should know which is input, which is output. You know what I meant? As a system engineer, please don't put, So please don't put your output at the input. So basically, you should know which is input, you should know output. And then nobody will put amplifier after output. So you should be, logically thinking what are the things involved. Well, I will teach you how the signal propagates. So you will be able to connect it easily. So there are 10 blocks. So on the top, you will see these are the major blocks, and then you will be connecting this to here, and so on. And after connecting, then you will see, so that is this one, that is this part. When you open this top schematics, that's what you see here. And then when you, on the LMS, you will see a folder. So that is called a DSO project template. And then you download this DSO template, and then when you open it, you will see like this. When you open it, so you can see DSO PCB. So this is a DSC PCB design file. Then here you can see 10 major blocks: ADC block, clock block, control, counters, CPLD, front end, input output, RAM, top, then trigger. So when you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, but 11, did I make a mistake? No, it's only 10 blocks, but the top one is the total block level diagram. You know what I meant? Means all these remaining 10 blocks are connected and shown on the top level diagram. So when you please download this file template from the LMS, and when you click it, you will see like this. So 10 blocks, and then this is a top level diagram where you will be connecting all the blocks. And then this is for designing the PCB. Then project template. So suppose when you click DSO underscore ADC on Altium. So when you open it, then I'm going to click maybe here. DSO underscore ADC. So when you click it, you can see, you will see some part already done, but some part we haven't done it. So you have to design the circuit for the missing part. So, but then you might be unhappy. When you click RAM, you will be very happy because all the RAM things we already did it for you. Because we know that it takes, lot of time if you give you an empty folder. So that's the reason we are giving you some help. Plus RAM design is not a big thing. From the data sheet you get all these connections. So, but then still please understand, though we have provided the connections, don't take it as a block level diagram, because then you will be losing some understanding from the DSO. But then when you take a front end, you don't have anything at all. See, you have to design all the circuits of the front end, which includes some clamping circuit. We will give the specification, amplifier, filter, all these things in the front end. You know what I meant? So some part we give you, some part we don't give you. So you will need to create blocks, approximately 10, and connect them correctly in Altium to represent your DSO design in system level. That you will be doing in the top, this one. Here you will be designing 10. This is my first block, second block. So you will see when you see the template, and then you will see this is a top level diagram. And then when I click this one, then I will go to the next one, means the circuit level. And in each block, some we will be give some partly given. See here we have given this much schematics design, but you have to find what are the requirement here. And then some we already given the entire thing, some you haven't given anything at all. So you have to design the entire circuit. So definitely you will be able to do it. We give you actually more help. Then how do you know the signal flow for the DSO? Obviously we know that you are students, and then you don't have much experience, but then I'll be teaching you how the signal flows, and then the significance of each block. Why do we need a buffer there, or why do we need ADC? What is the trigger function? How the trigger function is working? Why do we need a CPLD? All these things I'll be teaching you, so that you will be able to connect it quickly and design the circuits. And then this is an example. So here you see, you don't need to literally connect it. You can name something here, maybe A, and then here you can say that okay, A is coming here. You know what I meant? You don't need to connect it, because sometimes that is not possible. When you have so many connections, it is not possible to literally connect from here to here. So you can just put it here and then only just take it out, and then you define like some name, VCCA or something, then you put one here and then say VCCA is coming here, like that, when you have so many connections. Then after you design all these circuits, then what you do is you go to the DSO PCB part, this one. So here then you will get a PCB design part. Again, when you click here in the PCB, so that you click it only after designing all the circuits, including the footprint. Then most of the footprint we will be giving, so that you don't have to design. I think only one we will ask you to design, because again, based on my capstone experience, some student couldn't design a footprint. I was very unhappy. Then asked me some help. Then obviously I helped, but then I thought, okay, I will include in the ESD one footprint you have to design, so that you know how to design a new footprint. So footprint means when you have IC, so for example, so different packages are there for IC. So this is an example like SOIC. So there are, so you can see, so this IC, so this is a package footprint. See, this IC got this type of footprint, and then so you have to make your design as per this footprint. So surface mount, some surface mount means you are not making through hole, but then surface mount got a SOIC package, ST package, and then that got footprint. So here the IC should be exactly fitting in. So they will give you, so this is a footprint. Then if this is a IC LM741 you are using, on the Altium you will be designing, oh, this is 6.50 millimeter, and then this is 5.6, and then this each leg, that is 0.51, because then only you will be able to put in the IC on the PCB. But then if you know the footprint, sometimes you already get in the library the footprint of LM741, then you can just take from the library and put it easy for you. So that's the reason we will be giving you the footprint library for almost all the components except maybe one, so that you can learn it how to design a footprint. Because when you are working in a company, you can't say that footprint is not available, I can't design. Maybe I have to go to the university and do one more subject about footprint design. So that is not required. So that is the reason I have incorporated, so that you can design a footprint by yourself. But most of the footprint is given. See, your life is easy. And then we will give you the dimension of the PCB. It's not like that you design a big PCB and carry in your big bag. So it should be compact. We will give you the space, and then you can design accordingly. Then again, don't get stressed out when you hear all these things. If you are not keen in, like if you are not an expertise or you don't have much background in the electronics, you don't have to be getting stressed out after hearing, because this is like a semester-long project, not like other labs. So you got plenty of time to learn this system design. No, we will give you 2 PCBs. But if you make mistake, the mistake will be on the both. So why we give you both is because we got this kind of microcontroller. The pins are very, very close. So if you make some mistake, then you can solder the other one. So that we will give you some tips how to solder it. Yes, please.
So about the footprint, since we're designing our own footprint for one component, so what if we combine to the manufacturer doesn't?
In the sense, because this footprint means when you are designing a footprint, so you will be designing a footprint, because this is a design, the manufacturer got all the footprint of ICs, because it's called SOIC. So you might be designing an SOIC. So when if I am manufacturing some IC, then I have to follow some rules. There are some available guidelines how to make a footprint. Like then I can't make an arbitrary footprint. It should be from kind of available, like SOIC, ST, some footprints are there. So I should be adapting that footprint for my design. Then when I make the IC, sometimes what will happen is when I make my own amplifier IC, so I am producing amplifier IC in my company. Then in the first amplifier IC, I have decided to make a LT Spice model. LT Spice model means when you go to my website, you can download the LT Spice simulation model. And then you can just download it, connect the resistances, and you can simulate my amplifier. But then I will give you the footprint, because when you design it, I will design SC, ST, all the available footprint. I will post it on the website so that you can download and use it. So that is easy. Or I will contact Altium or those guys and say that please include my footprint, so that when you use it or update it, you get it. Then maybe in my second version IC, I will have maybe SOIC, but then I will not provide the footprint. But then you can check in your library it is there, or if it is not, you can modify an existing one if there is a little bit modification. Then I might not give you the LT-SPICE model. Then you have to write an LT-SPICE model in order to simulate. You know what I mean? LT-SPICE also you can't take it granted, because you can simulate only if the code is available for a particular amplifier. If you don't have the code available, you will need to write a code for the LT-SPICE. You don't know that one? Because most of the time you go to the library, pick up on IC and then simulate here. But then that code is available. If you don't have the code, you have to write it. But in our case, you don't have to write any code in the LT-SPICE, because we are using amplifier from the library. Yeah, for answer to your question is the manufacturer, as a IC manufacturer, they will be following some guidelines. Accepted footprints are there. So that only. So the modification that you have to make is maybe SOIC, but then there is a small modification. Maybe you are using a guard ring, something like that. I'll tell you, what is a guard ring. Then you may have to do modification. Otherwise, it will be standard. Yeah, so that is all about about the file. And then finally, you will be designing a PCB, something like this. You have to place the components neatly, and then we will fabricate 2 PCBs. Oh, sorry. Yeah. So then you will be getting a PCB something like this. Then you design it, place the components, and then you will be designing a PCB. And then we give you 2 PCBs, and then we also will give you a components kit so that you can solder the components. So then the first report, so we don't have any mid-semester test for the subjects. So that's a good news. We don't have any mid-semester test. And so you have got 2 submissions, major submissions. So the first submission is the DSO front-end simulation report. So DSO front-end simulation report means you will be simulating the front end. We can't simulate all the DSO on LT-SPICE, because DSO got RAM, DSO got ADC, DSO got DAC, all these things, pretty difficult to simulate on LT-SPICE. What we can simulate is the front end. So front end means input clamping and buffer. I will come to that point. Input clamping circuit and buffer circuit, anti-aliasing filter. So we will be designing a low pass filter. Then DC level shift and gain circuit, and then this will be connecting to ADC. So just before the ADC, so this is a front end. So you will need to design the circuits and find frequency response, input impedance, etc. We will give you the instruction. So that is the first submission. Then second submission is your PCB Gerber file for fabrication. So there are only 2 submissions. There is no mid-semester test. So first one is a DSO front-end simulation report, means you will be designing all these circuits, and then you will be simulating, and the simulation results will be attached along the report. Then we will give you the specification. Then you have to match those specifications for the front-end design. So that will be marked. And then after that, couple of weeks later, you have to submit your entire PCB design, Gerber file, that we will be sending out for fabrication. So there is no mid-semester test. Then all these deadlines, how much percentage we will post it on LMS, how much percentage this will carry. Then if your front end is not working, then we will definitely write to you, and then we will give you feedback. It's not meeting, and if it is there is a problem, even in your PCB, we will be quickly checking your Gerber files. Whether there is we will be able to find out the obvious mistakes, like some connections missing in your final design. But if you are making some footprint, you are making instead of 0.5, if you are making 0.2 mil, we may not be able to find it. You know what I meant? Because we don't have that much time, because we got around 100 PCBs, and then because we have to fabricate quickly. So, but if you are making some connection mistake, we will find out and let you know so you can correct it, because we don't want your PCB not working. Then, so now we will go to operation amplifiers. Again, it is kind of a continuation from ECD, because in the ECD we have studied internal blocks of operation amplifier. so that you are not scared of operation amplifiers. But then here what we are doing is when you are a system engineer, we don't need to know everything inside the operation amplifier. You know inside what is happening, but we can use operation amplifier as a black box. So because we are using only block level things, and then we will be using operation amplifier for designing amplifiers. See, it's interesting. Operation amplifier is made of so many transistor amplifiers. Then you are using that block for making another amplifier. You know what I meant? So you will be using operation amplifier for making amplifiers. But same time, operation amplifier has amplifier stages made of transistors. So in the ECD we discussed about the simple operation amplifier, and that is the reason operation amplifier got two inputs, inverting, non-inverting. Operation amplifier, if you come here, you got non-inverting, inverting. See, inverting, non-inverting. See, LM741, non-inverting, inverting. You got two inputs because operation amplifier input is a differential amplifier. So differential amplifier got two inputs, which we already studied in the ECD. And yeah, so operation amplifier as a black box. In order to use operation amplifier, the good news is you don't need to know everything inside the operation amplifier. You can use as a black box. So I'll tell you how to use operation amplifier as a black box. So operation amplifier is made of many transistors, diodes, resistors and capacitors in integrated circuit technology. Then they are making an operation amplifier in order to get the following characteristics. An ideal operation amplifier has got following features. So if you consider your operation amplifier as an ideal, infinite input impedance. So input impedance is infinity. So then you have to think. So input impedance is infinity. Then you should not stop there. As an engineer, you should be thinking a bit more further. So what are the implications? You know what I meant? Because most of the time you just stop there. You heard, yeah, input impedance is infinity, that's all. But then you should not stop there. You should be thinking further. What is the implication as a system engineer? If your input impedance is infinity, you can't put any current inside. You know what I mean? Your current flowing is zero. So that is the reason here I have shown your input current is equal to zero for ideal operation amplifier. Means no current is flowing into the operation amplifier because you got infinite input impedance. We will come to that point. Infinite gain for differential input. So it got infinite gain, zero output impedance. So here there is no output impedance, so that you are not losing any voltage here as a drop. Infinite frequency bandwidth. So this gain is not depending upon the frequency of the input signals. Input current equal to zero. That is because of the infinite input impedance. Then CMRR infinity. What is CMRR? Common mode rejection ratio. So that we already know when you have common mode signal, means when you connect the same signal in the inverting and the non-inverting terminal, same signal, your output should be equal to zero. But that happens only in the ideal operation amplifier, which we already studied in the ECD. CMRR. How many of you not remember? How many of you not remembering CMRR? Okay, but did you take ECD? Then we have to enroll you for ECD. But when you make an operation amplifier, your aim is hitting all these ideal values. But in the realistic case, for example, for LM741, you will be getting input impedance 2 megohm. You are not going to get infinity, but you get around 2 megohm. Then large differential voltage amplification. Amplification is still big one. 200 volt per millivolt. That's a big value. Output impedance not going to be 0, 75 ohms. See, output impedance 0, but you are getting around ohms, 75 ohms. Frequency bandwidth only 1 megahertz. So if you are operating above 1 megahertz, what will happen is you don't get any gain. When you become 1 megahertz, still it is unity gain. Current, input current is 0, but input current is 500 nanoamps, very, very small. CMRR 100 dB. Very, very big value, but still it is not infinity. So ideal value of CMRR is infinity, but then you are not getting infinity. So these are the realistic values. Then what are the op-amp characteristics? So in order to understand the op-amp, you will be familiar with input current, offset current, input impedance, common mode input range, differential input range, output impedance, output current maximum, asymmetric current sink sourcing, internal compensation, input voltage offset CMRR and PSRR. PSRR is the power supply rejection ratio, and then input voltage and current noise. So these are some parameters. Again, you don't have to look at all the parameters because you have to prioritize your design. Look at the important ones for you, and then remaining things, I don't mean that to neglect it, but then you have to prioritize. So op-amp circuit applications, I don't think you will find something without operation amplifier these days. Pretty much everywhere, you can write almost all the applications, you will be using operation amplifier. Amplification, such as amplification, filtering, comparators, level shifters. Then dB, so why do you use dB? Because this is also an important point many students fail to understand. Why do you need a dB scale? So in the operation amplifier, when we plot some gain, sometimes we will be using dB scale. So why do you need a dB? With the dynamic circuit voltage gains ranging anywhere from 1,000,000 times to smaller in one section of the circuit to next, it is often easier for us to express voltages, currents and gains in decibels. So why do we need dB? So dB means you are studying some variation. This is a simple thing. So people sometimes, when you go to industry, they will ask, why do you need dB scale? And I have seen, some of them didn't understand the concept. Why do you need dB scale? dB scale means you are doing some characterization. Your variation is somewhere 1, somewhere it is 100, somewhere it is 1000, somewhere it is 10,000. But then you want to plot everything on a same graph. If you plot in dB, you can make sense of it. You can plot everything together. So that's the reason we are using dB. So that's the reason here with the dynamic voltage gains ranging anywhere from 1,000,000 times smaller in one section of the circuit to the next. See that, so you can represent in dB. Then operation amplifiers. So as I said, ideal operation amplifier got infinite input impedance. So when you have infinite input impedance, so if you draw a small signal, what will happen is this is your V in 1, this is your V in 2. So V in 1 is connected to the positive terminal non-inverting, this is inverting, and then because you got infinite impedance, see this part is open because of like a MOSFET. This part is open, and then here you got A0 and V in 1 minus V in 2. So before going to that one, before go in depth, I want to show you one operation amplifier. So when you see the operation amplifier, I'm going to take LM741. So when you take LM741 operation amplifier, so So this is LM741 operation amplifier. As I said, you got this is a non-inverting, which we already discussed. Non-inverting. This is inverting input. So non-inverting means when you connect a signal here, if it is a positive cycle, in the output you get the same, not inverting. Inverting means if you connect a signal here, at the output you will get an inverted signal. So that is the reason this is inverting. Then when you get this operation amplifier, because we got some students didn't do ECD, but then that's the reason I am explaining this concept again. So operation amplifier can be operated in two ways. So first one is open loop, second one is closed loop. So what are the differences? We already studied in the ECD. So open loop means you take the operation amplifier, this is a non-inverting, so here you can connect a signal. Maybe this you can ground it, inverting. Then you take output from here. Obviously you will be connecting here some power supply, maybe plus 15 volt or plus 5 volt, and then offset pins, we don't, this offset is just you can change the DC shift here by changing this offset. If you got some offset at the output, you can use these pins to correct it. Anyway, we don't have to worry about it. And then here maybe you can connect to minus 5 volt. Then when you connect a signal in this open loop, when you connect, this is called open loop. So when you connect a signal like this is called open loop. Means there is no feedback. So open loop or no feedback. So what is the meaning? So can you make an amplifier like this? So maybe this one is I am going to connect maybe 1 millivolt signal here. So my question is what is the voltage here?
10 volts, I guess. Full voltage, 10 volts.
It's a 10 volt.
Gain is infinite, so full signal should come here.
Yeah, so this will hit the power line, the rail, positive rail.
Plus 5.
So here it will become plus. Why? Because when you take the operation amplifier, then you will be seeing the data sheet, because this is operating in the open loop mode. In the open loop mode means there is no feedback, and then you will be looking at this. See, in the operation amplifier they have given open loop signal differential voltage amplification. So differential voltage is coming because you are getting inverting and non-inverting. You are applying signal this point with respect to this point with respect to this point. And then what they have done is open loop. See, you have to be careful with this term, open loop gain. So then they have plotted open loop versus frequency. And then what they have done, so they have done something pretty much like this. If you connect a 1 millivolt, the problem is suppose the signal frequency is 10 hertz. If you are connecting a 10 hertz signal here, then I can find out, see, 10 hertz. So what is the gain? It's around 100 dB. So 100 dB is a very big number, and then you are getting 1 millivolt into 100 dB means it will hit the rail, plus 5 volt. And then so here in this open loop mode we are making use of the open loop gain. See, that is called open loop gain. So that is called open loop gain. And then how they have made this plot? How they have made this plot is this voltage they will make very, very small, maybe in a few microvolt, and then they vary the frequency from 0 hertz, and then they vary the frequency to very big number, and then they keep this microvolt signal amplitude constant, and then they measure the gain, and then they plot it. So when they plot it, you can see when the frequency is increasing, obviously your gain is decreasing, and then this is an open loop, so means there is no feedback. They have measured is something like this. But then can you use this one for amplification, open loop mode?
Depends on the frequency. Maybe for high frequency you may.
Yeah, but then here in the open loop the problem is you can see your gain is decreasing when you increase the frequency. So maybe you can use this for 10 hertz, maybe it's okay, 100 dB or up to here, maybe 8 hertz might be good to use as an amplifier. But then again the question is you can amplify only a very, very small voltage, because otherwise what will happen is even microvolt, what will happen is it can hit the rail. So when you design an amplifier, then here issue number 1, if you are using this as an amplifier, bandwidth is a problem. So you can't have more than 8 hertz. Then second one, you mostly hit the rail because of the open loop gain. So this open loop gain is already set inside. So you don't have any control of the gain. Then so firstly your bandwidth is limited because of this reason. Bandwidth is limited. Second reason, your gain is very, very high. You don't have any control. And then you have to adjust your input in order to match it. So actually you can't make a good amplifier in the open loop. In the open loop, then what is application? Have you seen any circuit operating in open loop?
Yes, an amplifier I have not heard of.
Not amplifier, any other circuit.
Other circuit you can have maybe a fridge or a rheostat where you just set the resistance. Like you want this much heating, so you put that setting and it operates.
But then there maybe you may have feedback.
And you could use a comparator.
Yeah, comparator is an example. So in the comparator what it does is it is comparing two signals. So in the comparator, comparator means you take an operation amplifier, then this is positive, this is negative. So you want to make, as I said, you want to compare two signals. You want to have an output when the input is exceeding some voltage. So what I can do is I will connect here 1 volt. And then what I can do is here I can connect a varying signal like this. So 0 to 1.5 volt. And then if I connect here plus volt, then 0 volt, ground, then this output, what will happen is it will be, so this is my waveform. So the waveform is rising like this, 0 to 1.5 volt, and then this is the output. So this is the output, so this is the input. Then what will happen is your input is increasing, then your output will be 0, because here when it is this input is greater than this input, so that is around this region. So when you dot like this, then this output voltage will go up to the 5 volt, and then it will stay there. When again your input is falling below 1 volt, then it will come down like this. So this you can compare the voltages. So that is an application. So this is called a comparator. So comparator operates in open loop mode. But then amplifier, we will be using closed loop. So what do you mean by closed loop? So closed loop means again same operation amplifier. So I am going to get the LM741. Then this is the pin number 1, 2, 3, 4, 5, 6, 7, 8. And then this, see, when you have the IC, you will see one kind of a notch here, something like a dot or something. That is, you should be counting 1 from there. 1, 2, 3, and then it will be counting 4, then 5 will come here, 6, 7, 8, something like that. And then here, you already saw the pin number 2 is, so the pin number 2 is the inverting, so negative. Pin number 3 is the non-inverting. So that is the reason. And then pin number 6 is the output. So what do you mean by closed loop? So closed loop means then I will be connecting maybe my signal here. So that is a signal. But then what I will do is, so I will be connecting the signal here. Then I connect this output back to the input. So this is called a closed loop or with feedback. So there is a feedback, and then the open loop there is no feedback. So this configuration with the closed loop or feedback we use for amplification. So we will study the advantages in the coming lectures. What are the advantages when you have a feedback? So it can increase the bandwidth, and you have the control over the gain now. When you have a feedback, actually you can, by putting some resistance in the feedback loop, you can design, I want a 10 gain, I can 20 gain, you know what I meant? So you have the control over it. Then I will be discussing more about in the coming lectures. So what you have to understand is op-amp you can operate in 2 modes. One is open loop, no feedback. Second one is closed loop with feedback. Open loop got some applications like comparator, but not used for making amplifier. Then when again coming to feedback, there are 2 types of feedback. Again we will study. So this feedback is called a negative feedback because your output you are connecting to the inverting terminal. If you are connecting your output back to the non-inverting terminal, it is called positive feedback. So we will study those slides. Maybe some refreshment is required. We already studied some part in the ECD, but we will going through again in bit more detail. And then for operation amplifier, the output. So we can write the output of operation amplifier as the following. So the output voltage equal to A0. So this A0 is called open loop gain. Means when there is no loop, what you have seen on the data sheet, the gain 100 dB. So that is an open loop gain into V in 1 minus V in 2. So this is a typical output for operation amplifier. Open loop gain into V in 1 minus V in 2. So when you are operating like something like this with no feedback, you know what I meant? And then A0 is open loop gain. So open loop gain means you can't change it. Why? Because when they designed, they already designed all the resistors and they set the gain. Then operation amplifier, this is non-inverting terminal input, inverting input. And operation amplifier also you can operate with respect to inverting with respect to non-inverting or in the differential mode, differential signal. So we will study again differential signal. So differential means VD. What we have applied is V positive minus V negative. So that will be going to the operation amplifier. So when V positive equal to V negative, then your VD equal to 0, then V out equal to 0 for ideal operation amplifier. But in real operation amplifier, what will happen is because of the common mode ejection ratio, even if the voltages are matching here, it will not be 0 here. That is the reason, even if you got noise here, then it is not going to cancel out entirely here because of the CMRR not infinite, which we studied in the ECD. And then now what we have to design is a phase shift. Phase shift means when you connect a signal to the inverting terminal, the output will be inverted. When you connect your signal to non-inverting, the signal will be same, phase is same, not inverted. So 0 degree phase shift change between V output and VD. Then operation amplifier inputs. As I discussed, for operation amplifier, when you connect your signal to the non-inverting terminal, and then you can ground the inverting. So this is called a non-inverting connection, non-inverting. And then what is happening is your signal, you get some amplification. This again in the open loop, as I said, but the signal polarity is same. You are connecting a very, very small signal here, and then you may get amplified one, provided this is very, very small, because this gain is very, very high. Then 0 degree phase change. But then for 180 degree phase change means if you are connecting signal to inverting terminal, then you get signal inverted. No matter it is with feedback or without feedback, inverting means your signal will be inverted. So operation amplifier inputs. So if you short it, then the question is you are connecting positive and negative shorted, and then you are connecting a common input. Then what will be the output? Yeah, ideally 0, but then you don't get 0 because of CMRR is not infinity. Same voltage source is supplied at both the terminals. Ideally, two inputs are equally amplified. Output voltage is ideally 0 due to differential voltage is 0. Practically, a small output signal can still be measured because of this common mode rejection ratio, which we studied in the ECD. Common mode rejection ratio, that is equal to differential gain by common mode to differential mode conversion, if you recall. And then because of the non-ideal nature of this current source, and then even these resistors might not match in the input part of the differential amplifier, that is the input to the operation amplifier. Yeah, just so that's the reason in the data sheet you will see high CMRR. People might be looking for a low noise amplifier. They want to amplify some very small signal, then you will be looking for high CMRR amplifier. Then another concept is, this is one of the important concepts in the operation amplifier, and virtual short. So what do you mean by virtual short? So if you know virtual short, you can maybe understand almost 60% or maybe 70% of the operation amplifier circuits, because most of them got negative feedback. So if you know the concept of virtual short, so what do you mean by virtual short? I did not understand as a student when I learned for the first time operation amplifier the concept of virtual short. But because of that I couldn't analyze some circuits, but later when I understood, I could analyze most of the circuits. It's a very simple, even amplifier, how op-amp is amplifying, I can explain using virtual short. We don't need the equations to explain how operation amplifier is amplifying. So what do you mean by virtual short? Virtual short means I'm going to take a negative feedback as an example. So this is an operation amplifier. Then your V out, which is equal to A0 open loop gain into V in 1 minus V in 2. I can write V in 1 minus V in 2, which is equal to V out by A0. Do you agree with from this equation? But if you got A0 open loop gain, as I said 100 dB, or say this is infinity, very, very high, then you can say V in 1 equal to V in 2. So the idea is when you are connecting a signal here, operation amplifier will make sure that this signal is identical to this signal in the voltage. So that is called virtual short. Virtual short means there is no short between this point and this point, V in 1 and V in 2, but it will make sure that the voltages are same, almost same, because your open loop gain is equal to infinity. So V1 equal to V in 2 does not mean both are shorted together. The real meaning is that when gain is very large, V in 1 minus V in 2 is infinitely small. Due to infinite gain of op-amp, the circuit forces V in 2 to be close to V in 1, thus creating a virtual short. So you don't need to understand many equations in order to understand the amplification. For example, I am going to show you how this is going to amplify without knowing any maths. So I don't know anything about the equations. So I am going to draw one operation amplifier. So now from here we are going to start the amplification. See, I got the operation amplifier, this is my operation amplifier, I got a negative feedback. Then the circuit number 1. So I am going to connect like this. Then I am going to give 1 volt here. So here I am going to connect plus 15, and then this I am going to give to 0. So what is output? So two answers, 15 or 1. Yeah, so 1 volt, because this actually, you got a negative feedback. So operation amplifier will make sure that this voltage equal to this voltage. Only when there is a feedback, not in the open loop. Because when you have open loop, if I connect 1 volt here, then what will happen is you don't get 1 volt here, because there is no feedback. No feedback. So when you have negative feedback, when you have got 1 volt to this one, then operation amplifier will make sure that this 1 volt. Then it's called virtual short. Using this one, I can design an amplifier. How? So what I will do is I will take here I will take only 1 millivolt, because I am going to amplify. Then here what I am going to do is I am going to make use of that operation amplifier as an amplifier. So then I am going to connect something like this. So this is 10K, or maybe you don't need 10K, 1K, this is 1K. If this is 1 millivolt, and then this is 1K, this is 1K. So then what is the voltage here? So if this is 1 millivolt, operation amplifier will make sure that because of the virtual short, this is 1 millivolt. Then what is the voltage here? How much? Well, this is a simple potential divider. So what is the voltage across this?
0.5 millivolts back.
So I will draw it like this. Sorry, I think I made a mistake. So like this. Yeah, so this is also 1K. So what is the voltage here? Then what is the voltage here? See, you got amplification. See, because of the virtual short, you can make an amplifier using the idea of operation amplifier. So what I have drawn is, so here you got an operation amplifier, and then here I am going to connect 1 millivolt, and then I am going to connect a resistor here, I am going to connect a resistor here, and then this is 1K, this is 1K, and then this is 1 millivolt. Operation amplifier will make sure that this is 1 millivolt, and then this is 1 millivolt. If this is 1 millivolt, you need a 2 millivolt here, because this is a resistor divider. So by varying this resistance, you can get different amplification. So here you are not using any maths, but then using the virtual short, you are making an amplifier. You know what I meant? So if somebody is asking you, explain the amplification of operation amplifier without equation, then you will be not, no, you are crazy, without equation, how can we get the amplification factor? Actually, you don't need. You need if you know the concept of virtual short, then you can say, yes, definitely using the virtual short, we can make the operation amplifier. We can make an amplification. Then unity gain amplifier. So next one is, that's what a unity gain. What do you mean by unity gain? The circuit shown below is called unity gain buffer. Note that the output is tied to the inverting input. Determine the output voltage if V in 1 equal to 1 volt. Open loop gain equal to 1000 volt. So somebody will ask you again the same question. Like here you said, then people can ask you, here you have connected 1 volt. Then here operation amplifier will make sure that this is 1 volt because of the virtual short. But then somebody can ask you, I understood from the virtual short concept, but now I want to see the maths. Can you derive it? Then you can say that it's not complex. So what you know is open loop gain is already given 1000. That is we can get from the data sheet. Then V out equal to A0 into V in 1 minus V in 2, because V in 1 is this one, V in 2 is this one. And then we can write V in 1 equal to V out, V in 2 equal to V out, because you are connecting this V out to the V in 2. So you can substitute V out with V in 2. And then V out equal to A0 into V in minus V out, because that is you shorted V out with V in 2, which is equal to A0 V in minus A0 into V out. Then V out by V in, which is equal to A0 by 1 plus A0. You can write it. But then A0 is 1000. See, 1000 divided by 1 plus 1000. So it's very, very small, and then that is approximately equal to 1. You know, when A0 tends to infinity means A0 equal to 1000, you substitute 1000 divided by 1001, so that is approximately equal to 1. So it is a buffer. So this V out by V in is the closed loop gain, because you got the feedback and then V out by V in, that is approximately equal to 1. So that's the reason you are getting unity gain buffer, you know, amplifier. And so op amp with supply rails. Op amp with supply rails means when you have when you are operating in the open loop gain, as I said, when you have very high input voltage, means very high means when you are operating in the open loop, very high means that is still in the microvolt. And then what will happen is it will hit the rail. You can't get any amplification, so that you can make maybe a sinusoidal small signal to square if you are operating in the open loop. The summary is, if you try to amplify, you want a big range for the amplification, then you should have maybe supply also bigger supplies, otherwise it will hit the rail. You get the clipping. Then non-inverting amplifier. So maybe I'll discuss a non-inverting amplifier in the next lecture. We already discussed a non-inverting amplifier, how it is amplifying. So now I am talking about the equations, and maybe this part I will discuss in the next lecture. Non-inverting amplifier. Yep.
Is there schedule a slide something? More convenient.
Yes, you please send me a mail. So I will ask our academic coordinator to include your mail for the teacher.
Because I am not being able to adjust it in my timetable.
No, I think maybe it is full. Maybe it is already full. So that's the reason I can't be able to adjust. So you please send me a mail, and I will.
Is it possible to adjust as one person? Because
No, I think I can ask her to add you there, and then it will be counted. Yeah, please send me. So I will ask our assistant to add you. Maybe you might have changed that.